again about electric double layer. So next speaker will be and he will talk about overlapping electric double layer FPGC catalyst. The thought.
Okay, good morning everyone. Today I'm going to talk about how does the substrate material alters the electronic and ionic properties of the nanoparticle. In personal life, I'm a dancer. 1 year ago, when I imagined a nanoparticle support on a substrate, I imagined a nanoparticle as the dancer, where the support is the floor to hold the dancer, to support the dancer. However, as I read into the literature, I realized that the support is not enough, but actively interact with the nanoparticle and quickly impact the catalytic activity. Therefore, the support should not be treated merely as a floor, but also the other lens. Here is an example of support modification. A group in Switzerland replaced the commercial carbon support by the newly fabricated boron carbide. And they witnessed an increase in the polarization curve of fused. At 0.9 volt, there is a 2.5 volt increase. And there are lots of factors in this supported nanoparticle system, including nanoparticle size, nanoparticle morphology, coverage, support conductivity defect, and we need to isolate among them. And as a theoretician, I find the electronic interaction particularly intriguing. This system is very complicated in that it has 3 components: the nanoparticle, the support, and the solution. And the 3 interfaces formed in between. At the solid-solid interface, electron redistribution occurs. At the solid-liquid interface, there is electrical double layers, where we need to resolve the potential distribution, ion-solvent electric field distributions. And the state-of-the-art quantum mechanical description for this electronic system is Conchamp density functional theory. It captures the catalyst support interaction, but it cannot treat solution part if it has a nanoparticle on top of that. If alternatively, one can include the effect of solution, but the nanoparticle should be taken out of the system because of the formidable computational cost. Therefore, I choose to use an in-house theory, density potential functional theory, recently developed by Professor Jun Huang. This theory, the electron density and electric potential are 2 core variables to solve for. This allows a continuous depiction of the metal solution system from the metal bulk to the solution bulk. The quantum mechanical nature of the electron is captured by this Thomas Fermi theory, while the classical charged fluids are captured by this modified Thomson-Boltzmann theory. And you can see the electric potential, the metal electron density, ion density, solvent density can all be captured. And in order to capture the distinct physiochemical properties of different metal materials, we made some methodological advancement to capture, to reproduce the experimentally measured work function, potential of zero charge, and differential double layer capacitance curve. This is a prerequisite of applying this DPFT to this supported nanoparticle system. Well, later we made use of this axial symmetry to perform a dimension reduction from 3D to 2D, and we are ready to have the results. So this is what we discovered. Some results challenge the conventional view in 2 aspects. In terms of electron redistribution, if a catalyst overlayer is on support, we know there are 2 different Fermi levels, so electron redistribution will occur, and there is a strong electric field at this interface, pointing from the positive charge to the negative charge. And because metal is a very good conductor, the spin is very strong, so the electric field is nothing in solution. However, in this real supported nanoparticle system, people adopt this conventional view, but in several years ago, Dr. Tobias Weniger proposed that, well, there might be outer surface charging at this particle as support interface surface. because the nanoparticle does not fully cover the support. And our result reveals that, well, because of this outer surface charging, there is an electric field surrounding the heterogeneous surface, and I will discuss it later in detail. The second aspect is for the differential capacitance at this heterogeneous surface. Take this polycrystalline silver as an example, where it has three different facets. The conventional view is, well, the differential capacitance for this total PC silver surface is just a weighted weighted average of the constituting single crystal facets. This is what they calculated by their experimentally measured data for single crystal facets. This is 50 years ago, and recently there's also another paper working on this kind of PC electrode. They simplify this PC electrode by this chessboard patterns, and they only remain two kinds of facets, blue and red. So what they show is this blue curve is for the blue facet, single crystal blue facet. This red curve is for this single crystal red surface. And what they predict is this three-peak shape for the total surface. And this is so we discovered something different. Okay, let's have a greater detail. Okay, so we analyzed 1 nanometer radius zero nanoparticle on gold support at this 1 millimole KPX6 solution at the global potential of zero charge. The global potential of zero charge is if we integrate over the whole volume, the total number of cation concentration is equal to the ionic concentration. That means there's no charge excess in the solution phase. And we further introduce this local net ion concentration by subtracting the ion concentration from the cation concentration. So positive means there's more cations, negative means there's more ions. And here's what we show. Despite the potential is controlled at the global potential of zero charge, there is charge separation in the solution phase. There's more ions in the silver particle top, there's more cations in the gold surface. That means, well, here the potential is more positive, so ionic accumulation. Potential is negative because so that the cation will accumulate here. And this is evidenced by electric field pointing from the positive potential region to the negative potential region. And this is a result. This is driven by the electron redistribution across the whole system because of the difference in Fermi level. So this electron redistribution is quantified by electron density difference at this constant charge condition. It is the difference in electron density of this catalyst support the combined system at its own charge neutral state minus the electron density of the catalyst along unsupported catalyst system at its own charge neutral state minus the electron density of the bare support system at its own charge neutral state. So this figure illustrates that once we put the nanoparticle on top of a support in electrolyte in its fabrication process, there is simultaneous electron redistribution across the system. There's more positive charge left here, more negative charge here, and it creates an electric field surrounding the heterogeneous surface and creates this charge separation in solution phase. Well, so here's a short conclusion of this slide. This slide shows constant charge condition. What happens under constant potential condition? What happens when we apply a certain potential to this system? Well, so to investigate the perturbation of the substrate on the ionic, local ionic and electronic properties of the nanoparticle, we first set a reference for local ionic properties. That is the unsupported nanoparticle at its own charge neutral state at this potential of zero charge of the catalyst. So we pick this point. This is 0.6 nanometer above the silver nanoparticle surface as the reference. Similarly, for the electronic properties, we choose the electron density at this point as the reference. And now we put the nanoparticle on top of the support and control it at the same potential, the same potential. What happens is, you see, there's blue shades here. That means electron depletion. There's some positively charge there because of their electron transfer between them. But intuitively, one might expect that above this positive charge surface, there might be ion accumulation. There should be more ions. But here, the red shade means there's more cation accumulation here. You see the 0.3 is 70 for this quantity. This contradiction can be rationalized by the electrical double layer overlap of this gold electrical double layer. Because gold is highly negatively charged, so it creates a very low, very negative potential region at this surface. So it attracts a lot of cations to the surface. Not only to this surface, but also here. So there's a double layer overlap between these two. You can see that the electronic and ionic properties are perturbed by this substrate despite at the same potential. The next question is, how can we tune the electric potential to recover the previous ionic state and to recover the previous electronic state? Why is it important? Because in electrochemistry we control everything by electric potential. We change the potential so that we have a certain ion concentration at our reaction plane. And a 0.2 volt difference in the onset potential of oxygen reduction, hydrogen evolution is significant. So we want to visualize this effect in the potential scale. So now what we do is we reduce the potential by 160 millivolts. What do you get? We recover the local electronic state. So here, it's the same as here. Despite that, the local ionic state is further deviated away from the previous case. You see? So that means their deviation are in opposite directions. What happens if we increase the potential by 340 millivolts? We recover the ionic state. You see, they are the same, but the local electronic state are further deviated from the original state. So you see that it exerts a 0.5 volt difference in this local ionic and electronic states. Okay, let's go to the next slide. The last result that I want to show is this differential double layer capacitance. This is very whole concept in electrochemistry because it is a fingerprint of electron. For planar electrode, it is frequently studied, but it received less attention for supported nanoparticle electrodes. So we first showed the CDL for planar electrode for silver and for gold. Synchrocrystal, like the planar electrode, homogeneous surface, it is like this. And intuitively, one would expect the average, the total response is like the average weighted average of the reference value. So you see this peak corresponds to this peak. These two local minimums corresponds to the two local minimums of the silver and gold. So yeah, this is my expectation. But what really comes out is like this. So the result curve recovers the feature, the double peak feature, and one local minimum feature of a homogeneous electrode. This is quite unexpected. So you see, the only one minimum corresponds to the global potential of the electron residing here. And electron redistribution tends to homogenize the heterogeneous surface by reshuffling the electron redistribution. Okay, to sum up, the metal support interaction strongly alters the local ionic and electronic properties by outer surface charging and double layer overlap. The differential capacitance of supported nanoparticle system remains double peak feature, as in the case of homogeneous planar electrode. And the advanced DPFT methodology is of general applicability to other heterogeneous nanostructures. I will thank my Dr. Fatou, my colleague, and my direct supervisor, Professor Wang, and Dr. Fermi. Thank you very much.
Yes, thank you, Yufan. Are there any questions? Yeah.
Very beautiful work. Thanks. So, how does the potential depend on the ionic strength of the solution?
Yeah, this is a very good question. And so the ionic structure. So here we vary the ion concentration and to test the effect of ionic strength. And here actually we show another set of data here. Okay. Just quickly explain this. This is for 0.1 millimole. It's very dilute, very low ionic strength. And if we go to 100 millimole, you see the effect is much damped. You see the color is very shallow. So the effect is more pronounced in low ionic strength scenarios. Yeah.
Okay. Are there any questions? It's gonna be like 10 minutes late, but we can save 10 minutes for lunch.
Yeah.
Unbelievable. Any more questions? So I mean, well, my question then, because the title says platinum carbon, and here results are gold silver. So can you transfer knowledge from gold silver to platinum carbon?
Yes. Yeah, thank you for this very nice question, and because I forgot to mention that. So we choose gold and silver because first we want to generate reliable results. We first need to make sure that our model is accurate. So we first calibrate our model parameters to reproduce these three properties for planar electron, for homogeneous planar electron. And because gold and silver has very good defined, well-defined reproducible data for differential capacitance curve, but platinum and carbon does not have. So we first choose gold and silver as a model system, and later we will expand this methodology to account for platinum and carbon chemistry.
Okay, thank you. Let's thank the speaker again.
I have 10 minutes for a coffee break. We can return back at half past 11.
你看你经历过下一个。
都结束了，你还在录吗？
你还在录啥？你是在录像还是？